the x value, if you look at it visually, it's helpful. So starting at 0 degrees, we're out here on the very end of the unit circle, so we're a distance of 1 to the right, so our cosine is going to be 1. Cosine of 0 is 1. Sine of 0 is 0. We go up to 30 degrees, and what we see now is, and we can get this again from equilateral triangles, getting the 30, 60, 90 ratios, and we'll see also 45, 45, 90 triangles, getting us other ratios. What we see here is that the cosine is rad 3 over 2, sine is a half. Clearly the cosine is going to be bigger than the sine, it's longer. Rad 3 over 2 is around 0.86, which is bigger than 0.5. We go up to 45 degrees, now it's an equilateral triangle, so they should be the same, and they are. They're both rad 2 over 2, which is about 0.707, which is between 0.5 and the rad 3 over 2, which was approximately 0.86. So here we are at 60 degrees, and so now sine, of course, is bigger than cosine because you're steeper. Now when we get up to 90 degrees, our cosine is 0 because we moved left or right at all, and our sine is 1. So once we get through the first quadrant, we start to positive. Now another good graphical way to keep track of these things, besides the x and y values being cosine and sine, is tangent is sine of y over x, which is basically your slope. So if you were in the first, you will have a tangent which is positive because this is a positive slope. If you're in the second or the fourth, your tangent will be negative because it's a negative slope. And so tangent is simply sine over cosine, so in this case it would be. Now we're at this, so to speak, between 180 and 270, between pi and 3 pi over 2. So our now is positive rad 3. And here our tangent is undefined because we're going up doing the remainder of the unit circle, at least this first revolution of it. We see our sine and cosine values, and of course we can get tangent and secant and cosecant cotangent from those. Keep track of what's going on in the first quadrant. Get an idea of where the functions are positive or negative based upon what quadrant you're in. Think in terms of x and y coordinates and slope, and you'll quickly be able to memorize what all of these things are. Now, this next rather busy sketch involves even and odd functions. So, first of all, let me explain what's going on here. An even function is a function such that f of negative x is equal to f of x. So if you plug in a negative value instead of the regular one, you get the same y value out. An odd function, f of negative x is negative f of x. So if you plug in a negative value, it's the same absolute value except it's in the opposite direction. So now looking at this little diagram over here in this part of the unit circle that I've snipped over here, we have this angle theta, and the sine of this angle is what's in red. It's the y value. Now we've got negative theta. The sine of negative theta is what's in green here. Now those are the same length, and yet the green one is the negative of the red one because it's going down instead of up. So therefore, sine of negative theta is equal to negative sine theta. That is, they're the same value, but one's positive, one's negative, and so therefore sine is an odd function. Now instead, if we look in terms of the x value for cosine, the cosine of theta is this black line here. The cosine of negative theta, also the black line here. So whether we put in a positive theta or negative theta, either way, we get this same distance here going in the positive direction. Cosine is going to be an even function. Now, even divided by even functions are even, odd divided by odd are even over odd or odd over even are odd. And so using those facts, along with this idea of, say, secant is 1 over cosine, the equation 1, y equals 1, is even, so even over even is going to be even, so secant will be even. Cotangent, for instance, is cosine over sine, which is even over odd, so that's odd. This is some polynomial examples of an even function and an odd function here. black and even and red is odd. And as far as when we get on to graphing these things, the symmetry that goes along with them is as follows. What we can see is we put a point up here and measure its coordinates, and if we calculate the negative x value, negative 3.28, and now the y value would be negative 2.15 as opposed to positive 2.15 because it's odd. So there's the point down there. All right, and look at how when we move it around, you see how it reacts to that. Now we'll do the y value for an even function. So for an even function, it's going to be the same value. And point forward, and now we'll trace, and you can see how these points move around. So as we can see, for the even one, the blue, we're symmetric about the y-axis with the red point. For the odd one, which is in green, we're symmetric about the origin. Symmetric about the x-axis wouldn't be a function, wouldn't pass the vertical line test, so we don't really go into that in this case. A few sample problems. This is just using the idea of coterminality of angles. If t is at negative 4 pi over 3, you want to realize that negative 4 pi over 3, you're going this direction, and you're back over about here, 3. And so then sine of 2 pi over 3 is its second quadrant, it'll be positive rad 3 over 2. The cosine, you're in the second quadrant, so it's going to be negative 2 over rad 3 secants 1 over cosine, negative 2, cotangents 1 over tangent, negative 1 over rad 3. There's really no reason to rad, it doesn't really do much. Just trying to simplify, again, using coterminality. 3 pi is the same as same location as 3 pi minus 2 pi, because you go around the unit circle, that's all the way to 3 pi. We end up at the same spot if we just go around the half turn. So sine of 3 pi is the same as sine of pi, and since we haven't gone up or down at this point, the y value is 0. In this case, what we have going on here is we're told that the sine of t is 4/5. So what I do is I just drew in the first quadrant, it could be the second quadrant, but it doesn't matter here. I drew in the first quadrant an angle t in blue, and I make this length 4/5 because it's a y value. We want to find out values for sine of pi minus t and sine of t plus pi. So if this angle here is t in blue, I can write this same angle over here, t in green. Those would be congruent angles. And so pi minus t is given by this angle here. And so the sine of that angle is going to be this distance here, which as we can see is the same as the distance in blue, will also be 4/5. Now sine of t plus pi is half of a revolution because 2 pi radians is a full revolution, so pi is half. So if we're at an angle here of t in blue, we go t plus pi, we get down here. And now you can see that the sine for this angle, which goes all the way around to here, is going to be given by this black line here, and that's the same length but going down, so that will be negative 4/5 instead of positive 4/5. And the last thing to look at is this idea of type of problem where we have a line y plus 3 halves x equals 0, and y is positive. Want to find the 6 trig values, and the way you set it up is you draw a slope of negative 3 halves approximately. Y equals. We'll put the 3. Using the Pythagorean theorem, we get rad 13, and now we simply using SOHCAHTOA, sine being opposite over hypotenuse, cosine adjacent over hypotenuse, and so on. And here I've rationalized it, though it's not really that necessary to do that.